Hello, and welcome to the Data Engineering Podcast, the show about modern data management. When you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With 200 gigabit private networking, scalable shared block storage, and a 40 gigabit public network, you've got everything you need to run a fast, reliable, and bulletproof data platform. If you need global distribution, they've got that covered too with worldwide data centers, including new ones in Toronto and Mumbai. And for your machine learning workloads, they just announced dedicated CPU instances. Go to dataengineeringpodcast.com/Linode, that's Linode today to get a $20 credit and launch a new server in under a minute. And don't forget to thank them for their continued support of this show. And to grow your professional network and find opportunities with the startups that are changing the world, then Angel List is the place to go. Go to dataengineeringpodcast.com/Angel to sign up today. And you listen to this show to learn and stay up to date with what's happening in databases, streaming platforms, big data, and everything else you need to know about modern data management. For even more opportunities to meet, listen, and learn from your peers, you don't want to miss out on this year's conference season. We have partnered with organizations such as O'Reilly Media, Dataversity, and the Open Data Science Conference, with upcoming events including the O'Reilly AI Conference, the Strata Data Conference, and the combined events of the Data Architecture Summit and Graph Forum. Go to dataengineeringpodcast.com/conferences to learn more and to take advantage of our partner discounts when you register. And go to the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, read the show notes, and get in touch. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers. Your host is Tobias Macy, and today I'm interviewing Tim Ward about his thoughts on eventual connectivity as a new pattern to replace traditional ETL. And just as a full disclosure, Tim is the CEO of CluedIn, who is a sponsor of the podcast. So Tim, can you just start by introducing yourself?
Yeah, sure. My name is Tim Ward. As Tobias has said, I'm the CEO of a data platform called CluedIn. I'm based out of Copenhagen, Denmark. I have with me my wife, my little boy Finn, and a little dog that looks like an Ewok called Seymour.
And do you remember how you first got involved in the area of data management?
Yeah, so I mean, I'm I guess a classically trained software engineer. I've been working in software space for around 13, 14 years now. I've been predominantly working in the web space, but mostly for enterprise businesses. And around, I don't know, maybe 6 or 7 years ago, I was given a project which was in the space of what's called multivariate testing. It's the idea that if you've got a website and maybe the homepage of a website, if we make some changes or different variations, which variation works better for the amount of traffic that you're wanting to attract, or maybe the amount of purchases that a company makes on the website. So, I mean, using this, that was my first foray into, okay, so this involves me having to capture data on analytics. It then took me down this rabbit hole of realizing, got it. I have to not only get the analytics from the website, but I need to correlate this against, back office systems, CRM systems, and, ERP systems and PIM systems. And I kind of realized, oh God, this becomes quite tricky with the integration piece. And once I went down that rabbit hole, I realized, for me to actually start doing something with this data, I need to clean it. I need to normalize it. And, basically I got to this point where I realized, well, data's kind of a hard thing to work with. It's not something you can pick up and just start getting value out of straight away. So that's kind of what led me into the path of around 4.5, 5 years ago, saying, you know what, I'm going to get into this data space. And ever since then, I've just enjoyed immensely being able to help large enterprises in becoming a lot more data driven.
And so to frame the discussion a bit, I'm wondering if you can just start by discussing some of the challenges and shortcomings that you have seen in the existing practices of ETL.
Yeah, sure. I mean, I guess I want to start by not trying to be that grumpy old man that's yelling at old technologies. And I'm always this person that one thing I've learned in my career is that it's very rare that a particular technology or approach is right or wrong. It's just right for the right use case. And I mean, also you're seeing a lot more patterns in integration emerge. Of course, we've got the ETL that's been around forever. You've got this ELT approach, which has been emerging over the last few years. And then you've kind of seen streaming platforms also take up the idea of joining streams of data instead of something that is kind of done up front. And, to be honest, I've always wondered with ETL, how on earth are people achieving this for an entire company? Like ETL for me has always been something that if you've got 2, 3, 4 tools to be able to integrate, it's a fantastic kind of approach, right? But, now we're definitely dealing with a lot more data sources, and the demand for having free-flowing data available is becoming, much more apparent. And it was to the point where I thought, am I the stupid one? Like, I can't, if I have to use ETL to integrate data from multiple sources, as soon as we go over a certain limit of data sources, the problem just exponentially becomes a lot harder. And I think the thing that I found interesting as well with this ETL approach is that typically once the data was processed through these classic, designers, workflow DAGs, directed acyclical graphs, the output of this process was typically, I'm going to store this in a relational database. And therefore, I could understand why ETL existed. I could understand that, if you know what you're going to do with your data after this ETL process, I mean, classically, it would go into something like a data warehouse. I can see why that existed. And I think there's just different types of demands that are in the market today. There's much more need for, flexibility and access to data, and not necessarily data that's been modeled as rigidly as you do get in the kind of classical data warehouses. And I kind of thought, well, the relational database is not the only database available to us as engineers. And one of the ones that I've been focusing on for the last few years is this graph database. And I kind of, when you think about it, most problems that we're trying to solve in the modeling world today, they are actually a network. They are a graph. They're not necessarily a relational or a kind of flat document store. So I thought, this seems more like the right store to be able to model the data. I think the second thing was that just from being hands-on, I found that this ETL process, what it meant was that when I was trying to solve problems and integrate data, up front, I had to know what were all the business rules that dictated how these systems integrate, but what dictated clean data. I mean, you're probably, Tobias, used to these ETL designers where I get these built-in functionalities to do things like, trim white space and tokenize the text and things like that. And you think, but I need to know up front what is considered a bad ID or a bad record. You're probably also used to seeing, we've got these IDs, and sometimes it's a beautiful looking ID, and sometimes it's -1 or NA or placeholder or hyphen, and you think, I've got to up front in the ETL world define what are all those possibilities before I run my ETL job. And I just found this quite rigid in its approach. And I think the key kind of game changer for me was that, when I was using ETL and these classic designers to integrate more than 5 systems, I realized how long up front it took that I needed to go around the different parts of the business and have them explain, okay, so how does the Salesforce lead table connect to the Marketo lead table? Like, how does it do that? And then time after time, after weeks of investigation, I would realize, I have to jump to the exchange server or the Active Directory to get the information that I need to join those two systems. And it just resulted in the spaghetti of point-to-point integrations. And I think that's one of the key things that ETL suffers from, is that it puts us in an architectural design thinking pattern of, how am I going to map systems point to point? And I can tell you, after working in this industry for five years so far, that systems don't naturally blend together point to point.
Yeah, your point too about the fact that you need to understand what are all the possible representations of a null value means that in order for a pipeline to be sufficiently robust, you have to have a fair amount of quality testing built in to make sure that any values that are coming through the system map to some of the existing values that you're expecting, and then be able to raise an alert when you see something that's outside of those bounds so that you can then go ahead and fix it, and then being able to have some sort of a dead letter queue or bad data queue for holding those records until you get to a point where you can reprocess them, and then being able to go through and back populate the data. So it definitely is something that requires a lot of engineering effort in order to be able to have something that is functional for all of the potential values. And also there's the aspect of schema evolution and being able to figure out how to propagate that through your system and have your logic flexible enough to be able to handle different schema values for cases where you have data flowing through that is at the transition boundary between the two schemas. So it's definitely a complicated issue. And so you recently released a white paper discussing some of your ideas on this concept of eventual connectivity. And so I'm wondering if you can describe your thoughts on that and touch on how it addresses some of the issues that you've seen with the more traditional ETL pattern.
Yeah, sure. I mean, I think one of the concepts that behind this pattern we've kind of named eventual connectivity, and um, is there's a couple of fundamental things to understand. First of all, it's a pattern that essentially embraces the idea that we can throw data into a store, and as we continue to throw more data, records will find out itself how to be merged. And it's the idea of being able to place records into this kind of central place, this central repository, with little hooks, that are, or flags that are indicating, hey, I'm a record, and here are my unique references. So, obviously, with the idea being that um, as we bring in more systems, those other records will say, hey, I actually have the same ID. Now, that might not happen up front. It might be after you've integrated system 1, 2, 3, 4, 5, 6, that system 2 and 4 are able to say, hey, I now have the missing pieces to be able to merge our records. So in an eventual connectivity world, what this really brings an advantage is that, first of all, if I'm trying to integrate systems, I only need to take one system at a time. And I found it rare in the enterprise that I could find someone who understood the domain knowledge behind their Salesforce account and their Oracle account, and their Marketo account. I would often run into someone who completely understood the business domain behind the Salesforce account. And for the reason I'm using that as an example is because Salesforce is an example of a system where you can do anything in it. You can add objects that are, animals or dinosaurs, not just the ones that are out of the box. I don't know who's selling to dinosaurs, but essentially what this allows me to do is, when I walk into an integration job and that business says, hey, we have 3 systems, I say, got it. And if they say, oh, sorry, that was actually 300 systems, I go, got it. It makes no difference to me. It's only a time-based thing. The complexity doesn't get more complex because of this type of pattern that we're taking. And I'll explain the pattern. Essentially, what we do is you can conceptualize it as we go through a system, a record at a time or an object at a time. Let's take something like leads or contacts. And the pattern basically asks us to highlight what are unique references to that object. So in the case of a person, it might be something like a passport number. It might be a local personal identifier. In Denmark, we have what's called the CPR number, which is a unique reference to me. No one else in Denmark can have the same number. But then you get to things like emails, and what you discover pretty quickly in the enterprise data world is that email in no way is a unique identifier of an object, right? We can have group emails that refer to multiple different people, and not all systems will specify as if this is a group email or if this is an email referring to an individual. So the pattern asks us or dictates us to mark those references as aliases, something that could allude to a unique identifier of an object. And then when we get to the referential pieces, so imagine that we have a contact that's associated with a company. You could probably imagine that there's a column in the contact table that's called company ID. And the key thing with the eventual connectivity pattern is that although I want to highlight that as a unique reference to another object, I don't want to tell the integration pattern where that object exists. I don't want it to tell that it's in the Salesforce organization table. Because to be honest, if that's a unique reference, that unique reference might exist in other systems. And so what this means is that I can take an individual system at a time and not have to have this standard point-to-point type of relationship between data. And I think if I was to highlight kind of three main wins that you get out of this, I think the first is that it's quite powerful to walk into a large business and say, hey, how many systems do you have? Well, we have 1,000. And I think, good, when can we start? Now, if I was in the ETL approach, I would be thinking, oh, God, can we actually honestly do this? Like, as you could probably know yourself, Tobias, often we go into projects with big smiling faces, and then when you see the data, you realize, oh, this is going to be a difficult project. So that advantage of being able to walk in and say, I don't care how many systems you have, it makes not a lot of complexity difference to me. I think the other piece is that the eventual connectivity pattern addresses this idea of that you don't need to know all the business rules up front of how systems connect to each other, but then what's considered bad data versus good data. And rather that, we let things happen and we have a much more reactive approach to be able to rectify them. And I think this is more cognizant, or it's more representative of the world that we live in today. Companies are wanting more real-time data to their consumers or to the consumption technologies where we get the value, things like business intelligence, etc. And they're not willing to put up with these kind of rigid approaches of, oh, the ETL process has broken down. I need to go back to our designer. I need to update that and run it through and make sure that we guarantee that the data is in the perfect order before we actually do the merging. And I think the final thing that has become obvious time after time where I've seen companies use this pattern is that this eventual connectivity pattern will discover joins where it's really hard for you and me to just sit down and figure out where these joins are. And I think it comes back to this core idea that systems don't connect well point to point. There's not always a nice ID or this ubiquitous ID that we can just join two systems together. Often we have to jump in between different data sources to be able to wrangle this into a unified type of set of data. Now, at the same time, I can't deny that, there's quite a lot of work that's going on in the field of, ETL. You've got platforms like NiFi and Airflow, and you know what? Those are still very valid. They're still, they're very good at moving data around. They're fantastic at breaking down a workflow into these kind of discrete components that can, in some cases, play independently. I think that the eventual connectivity pattern for us, time after time, has allowed us to blend systems together without this overhead of complexity. And Tobias, there's not a big enough whiteboard in the world when it comes to integrating, 50 systems. You just have to put yourself in that situation and realize, oh, wow, the old ways of doing it are just not scaling.
And as you're talking through this idea of eventual connectivity, I'm wondering how it ends up being materially different from a data lake where you're able to just do the more ELT pattern of just ship all of the data into this repository without having to worry about modeling it up front and understanding what all the mappings are, and then doing some exploratory analysis after the fact to be able to then create all of these connection points between the different data sources and do whatever cleaning happens after the fact.
Yeah, I mean, one thing I've gathered in my career as well is that, something like an overall data pipeline for a business is going to be made up of so many different components. And in our world, in the eventual connectivity world, the lake still makes complete sense to have. I see the lake as a place to dump data. There I can read it in a ubiquitous language. In most cases, it's SQL that it's exposed. I don't know a single person in our industry that doesn't know SQL to some perspective. So that is fantastic to have that lake there. Where I see the problem often evolving is that the lake is obviously kind of a place where we would typically store raw data. It's where we abstract away the complexity that, now if I need data from a SharePoint site, I have to learn the SharePoint API. No, the lake is there to basically say, that's already been done. I'm going to give you SQL, and that's the way that you're going to get this data. What I find is that when I look at the companies that we work with is that, yes, but there's a lot that needs to be done from the lake to where we can actually get the value. I think something like machine learning is a good example. Time after time we hear, and it's true, that machine learning doesn't really work that well if you're not working with good quality, well-integrated data that is complete. So it's missing, nulls, and it's missing empty columns and things like that. And what I found is that we went through this in our industry. We went through this period where we said, okay, well, the lake is going to give the data science teams and the different teams direct access to the raw. And what we found is that every time they tried to use that data, they went through these common practices of, now I need to blend it. Now I need to catalog it. Now I need to normalize it and clean it. And you could see that the eventual connectivity pattern is there to say, no, this is something that sits in between the lake that matures the data to the point where it's already blended. And that's one of the biggest challenges I kind of see there is that, if I get, a couple of different files out of the lake, and then I go to investigate how this joins together, I still have this, this experience of, this doesn't easily blend together. So then I go on this exploratory, this discovery phase of what other data sets do I have to use to string these two systems together? And we would kind of just like to eliminate that.
So to make this a bit more concrete for people who are listening and wondering how they can put this pattern into effect in their own systems, can you talk through an example system architecture and data flow for a use case that you have done or at least experimented with to be able to put this into effect, and how the overall architecture plays together to make this a viable approach, and how those different connection points between the data systems end up manifesting?
Yeah, definitely. So maybe it's good to use an example. Imagine you have 3 or 4 data sources that you need to blend. You need to ingest it. You then need to usually merge the records into kind of a flattened unified data set. And then you need to, push this somewhere. So it might be a data warehouse, something like BigQuery or Redshift, etc. And the fact is that, in today's world, that data also needs to be available for the data science team. And now it needs to be available for things like exploratory business intelligence. So when you're building your integrations, I think architecturally, from a modeling perspective, the 3 things that you need to think about are what we call entity codes, aliases, and edges. And those 3 pieces together is what we need to be able to map this properly into a graph store. So simply put, an entity code is kind of an absolute unique reference to an object. As I alluded to before, something like a passport number, that's a unique reference to an object, but by itself, just the passport number doesn't mean that it's unique across all the systems that you have at your workplace. So the other is aliases. So aliases is more of like this email, a phone number, a nickname. They're all alluding to some type of overlap between these records, but they're not something that we can just honestly go ahead and just 100% merge records based off these. Now, of course, for having that, you of course then need to investigate things like inference engines to build up confidence on how confident can I be that a person's nickname is unique in the reference of the data that we've plugged in, these 3 or 4 data sources that I'm talking about. And then finally, the edges, they're placed essentially, they're there to be able to build the referential integrity. But what I find architecturally is that when we're trying to solve data problems for companies, a majority of the time, their model represents much more a network than the classic relational store or columnar database or document store. And so when we look at the technology that's needed to support this system architecture, one of the key technologies at the heart of this is a graph database. And to be honest, it doesn't really matter which graph database you use, but it is kind of what we found important is that it needs to be a native graph store. There are triplet stores out there. There are multi-mode databases like Cosmos DB and SAP HANA. But what we found is that you really need a native graph to be able to do this properly. So the way that you can conceptualize the pattern is that every record that we pull in from a system or that you import, it will go into this network or graph as a node. And every entity code for that record, i.e. the unique ID or multiple unique IDs of that record, they will also go in as a node connected to that record. Now, every alias will go in as a property on that original node because we want to probably do some processing later to figure out if we can turn that alias into one of these entity codes or these unique references. Now, here's the interesting part. This is the part where the eventual connectivity pattern kicks in. All the edges, i.e. if I was referencing a person to a company, that person works at a company. Now, those edges are placed into the graph and a node is created but is marked as hidden. Now, we call those shadow nodes. So you could imagine if we brought in a record on Barack Obama and it had Barack's phone number. Now, that's not a unique reference. But what we would do is we would create a record, a node in the graph that's referring to that phone number, link it to Obama, but mark the phone number node as hidden. And as I said before, we call these shadow nodes. And essentially you can see that as one of these hooks that, if I ever get other records that come in later that also have an alias or an entity code that overlap, that's where I need to start doing my merging work. And what we're hoping for, and this is what we see time after time as well, is that as we import System 1's data, it'll start to come in and you'll see a lot of nodes that are these shadow nodes, i.e. I have nothing to hook onto on the other side of this ID. And the analogy that kind of we use for this shadow node is that records come in, they're by default a clue. So a clue is in no way factual, in no way do we have any other records that are correlating to these same values. And our goal is to turn, in this eventual connectivity pattern, clues to facts. And what makes facts is records that have the same entity codes that exist across different systems. So the architectural key patterns to this is that a graph store needs to be there to model our data. And here's one of the key reasons. If I realized that the landing zone of this integrated data was a relational database, I would need to have an upfront schema. I would need to specify how these objects connect to each other. And what I've always found in the past is that when I need to do this, it becomes quite rigid. Now, I'm a strong believer in every database needs a schema at some point, or you can't scale these things. But what's nice about the graph is that one of the things that got really, or design patterns that it got really well, was flexible data modeling. There is no necessarily more important object that exists within the graph structure. They're all equal in their complexity, but also in their importance. And really pick and choose the graph database that you want, but it's one of the keys to this architectural pattern.
So one of the things that you talked about in there is the fact that there's this flexible data model. And so I'm wondering what type of upfront modeling is necessary in order to be able to make this approach viable. I know you talked about the idea of the entity codes and the aliases, but for somebody who is taking a source data system and trying to load it into this graph database in order to be able to take advantage of this eventual connectivity pattern, what is the actual process of being able to load that information in and assign the appropriate attributes to the different records and to the different attributes in the record? And then also, I'm wondering if there are any limitations in terms of what the source format looks like as far as the serialization format or the types of data that that this approach is viable for.
Sure, good question. So, I mean, I think the first thing is to identify that the eventual connectivity pattern and modeling it in the graph, the key to this is that there will always be extra modeling that you do after this step. And the reason why is because if you think about the data structures that we have as engineers, the network or the graph is the highest fidelity data structure we have. It's a higher or more detailed structure than a tree. It's more structured than a hierarchy or a relational store, and definitely we have more structure or fidelity than something like a document. And with this in mind, we use the eventual connectivity to solve this piece of integrating data from different systems and modeling it, but we know we will always do better modeling for the purpose fit case later. So it's worth highlighting that the value of the eventual connectivity pattern is that it makes the integration of data easier, but this will definitely not be the last modeling that you would have. And therefore, this allows flexible modeling because you always know, hey, if I'm trying to build a data warehouse based off the data that we've modeled in the graph, you're always going to do extra processes after it to model it into probably the relational store for a data warehouse or a columnar. You're going to model it purpose fit to solve that problem. However, if what you're trying to achieve with your data is flexible access to data to be able to feed it off to other systems, you want the highest fidelity and you want the highest flexibility in modeling. But the key is that if you were to drive your data warehouse directly off this graph, it would do a terrible job. That's not what the graph was purpose-built for. The graph was always good at flexible data modeling. It's always good at being able to join records very fast. And I mean just as fast as doing an index lookup. That's how these native graph stores have been designed. And so it's important to highlight that the upfront modeling, really, it's not a lot of upfront modeling. Of course, we shouldn't do silly things, but I'll give you an example. If I was modeling a skill, a person, and a company, it's completely fine to have a graph where the skill points to the person and the person points to the organization. And it's also okay to have that the person points to the skill and the skill points to the organization. That's not as important. What's important at this stage is that the eventual connectivity pattern allows us to integrate data more easily. Now, when I get to the point where I want to do something with that data, I might find that, yes, I actually do need an organization table which has a foreign key to person, and then person has a foreign key to skill. And that's because that's typically what a data warehouse is built to do. It's to model the data perfectly, so if I have 1 billion rows of data, this report still runs fast. But we lose that flexibility in the data modeling. Now, as for formats, and things like that. What I found is that to some degree that the formatting and the source data, well, you could probably imagine the data is not created equally, right? So for many different systems, they'll allow you to do absolutely anything you want. And where the kind of ETL approach allows you to, or kind of dictates that you capture these exceptions up front of, if I've got a certain looking data coming in, how does it connect to the other systems? What eventual connectivity does is it just captures them later in the process. And my thoughts on this is that, to be honest, you will never know all these business rules up front, and therefore kind of let's embrace an integration pattern that says, hey, if the schema in the source or the format of the data changes, and you kind of alluded to this before as well, Tobias, is, okay, got it. I want to be alerted that there is an issue with deserializing this data. I want to start queuing up the data in a message queue or maybe a stream, and I want to be able to fix that schema and a platform to be able to say, got it, now that that's fixed, I'll continue on with serializing the things that will now serialize. And these kind of things will happen all the time. I think I've referred to it before and heard other people refer to it as schema drift. And this will always happen in source and in target. So what I've found success with is embracing patterns where failure is going to happen all the time. And when we look at the ETL approach, it's much more of a, when things go wrong, everything stops, right? That the different workflow stages that we put into our kind of classical ETL designers, they all go red, 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 red. I have no idea what to do, and I'm just going to kind of fall over. And so what we would rather is a pattern where it says, got it, schema's changed, I'm going to log up what you need to do until the point where you've changed that schema. And when you've put that in place, I'll test it. I'll say, yep, that schema, that seems to be, I can serialize that now. I'll continue on. And what I find is that if you don't embrace this technology, you spend most of your time in just reprocessing data through ETL patterns.
And so it seems that there actually is still a place for workflow engines or some measure of ETL where you're extracting the data from the source systems, but rather than loading it into your data lake or your data warehouse, you're adding it to the graph store for then being able to pull these mappings out, and then also potentially going from the graph database where you have joined the data together and then being able to pull it out from that using some sort of query to be able to have the mapped data extracted and then load that into your eventual target.
I mean, what you've just described there is a workflow. And therefore, these workflow systems, they still make sense. They're very logical to look at these workflows and say, oh, that happens, then that happens, then that happens. They completely still make sense. And I still actually use, in some cases, I actually still use these ETL tools for very specific jobs. But what you can see is if we were to use these kind of classical workflow systems, you can see the eventual connectivity pattern as you described. It's just one step in that overall pattern. But I think what I've found over time is that we use these workflow systems to be able to join data. And I would actually rather throw it to an individual step called eventual connectivity, where it does the joining and things like that for me, and then continue on from there. You could, very similar to the kind of example you gave is, and that I've also been mentioning here as well, is there will always be things you do after the graph. And that is something you can easily push into one of these workflow designers. Now, as for an example of the times when our company still uses these tools out at our customers, I think one of the ones that makes complete sense is IoT data, and it's mainly because it's not typical in at least the cases that we've seen that there's as much hassle in blending and cleaning data. We see that more with operational data, things like transactions and customer data and customer records. That's typically quite hard to blend. But when it comes to IoT data, if there's something wrong with the data that it can't blend, it's often that, well, maybe it's a bad reader that we're reading off instead of something that is actually dirty data. Now, of course, every now and then, if you've worked in that space, you'll realize that readers can lose a network and they can have holes in the data. But I mean, eventual connectivity would not solve that either, right? And typically in those cases, you'll do things like impute the values from historical and future data to fill in the gaps. And it's always a little bit of a guess. That's why we're imputing it. But to be honest, if it was my task to build a unified data set from across different sources, I would just choose this eventual connectivity pattern every single time. If it was to have to a workflow of data processing where I know that data blends easy, then there's not a data quality issue, right? Where there is, you need to jump across multiple different systems to merge data. I just, time after time, have found that these workflow systems, they reach their limit where it just becomes too complex.
And for certain scales or varieties of data, I imagine that there are certain edge cases that come up when trying to load everything into the graph store. And so I'm wondering what you have run up against as far as limitations to this pattern, or at least alterations to the pattern to be able to handle some of these larger volume tasks.
I think I'll start with this. The graph is notoriously hard to scale. And most of the graph databases that I've had experience with, and you're essentially bound to one big graph. So there's no kind of idea of clustering these data stores with subgraphs that you could query across. So scaling that is actually quite hard to start with. But I think the limitations from the pattern itself, there are many. I mean, it starts with the fact that you need to be careful. I'll give you a good example. I've seen many companies that use this pattern and they flag something like an email as unique, and then we realize later, no, it's not. We have merged records that are not duplicates. And this means, of course, that you need support in the platform that you're utilizing, the ability to split these records and fix them and reprocess them at a later point. But I mean, these are also things that will be very hard to pick up in ETL, ELT types of patterns. But I think one of the other downsides of this approach is that up front, you don't know how many records will join. You're kind of, like the name alludes to, eventually you'll get joins or connectivity. And you can think of it as this pattern will decide how many records it will join for you based off these entity codes or unique references, or the power of your inference engine when it comes to things that are a little bit fuzzy, unique, or fuzzy IDs to someone, things like phone numbers and things like that. The great thing about this is it also means that you don't need to choose what type of join that you're doing. I mean, in the relational world, you've got plenty of different types of joins, inner joins, outer joins, left outer, left right outer joins, things like this. In a graph, there's one join, right? And so with that pattern, it's not like you can pick the wrong join to go with. There's only one type of thing. So it really becomes useful when, no, I'm just trying to merge these records. I don't need to handhold how these joins will happen. I think one of the other downsides that I've had experience with this is that, let's just say you have, system 1 and 2. And what you'll often find is that when you integrate these two systems, you have a lot of these shadow nodes in the graph, i.e., sometimes we call them floating edges, where, hey, I've got a reference to a company with an ID of 123, but I've never found the record on the other side with the same ID. So I have, in fact, I'm storing lots of extra information that, I'm not actually utilizing it. But I think the advantages of saying, yeah, but you will integrate system 4, you will integrate system 5 where that data sits. But the value is that you don't need to tell this system how they join. You just need to flag these unique references. And I think that the kind of final maybe limitation or thing that I found with these patterns is that you learn pretty quickly, as I alluded to before, that there are many records in your data sources where you think a column is unique, but it's not. It might be unique in your system, i.e. in Salesforce, the ID is unique. But if you actually look across the other parts of the stack, you realize, no, there is another company in another system with a record called 123, and they have nothing to do with each other. And so what these entity codes that I'm talking about, they're made up of multiple different parts. They're made up of the ID, 123. They're made up of a type, something like organization. And they're made up of a source of origin, Salesforce account 456. And so what this does is it guarantees uniqueness if you added in two Salesforce accounts, or if you added in systems that have the same ID, but it came from a different source. And as I said before, a good example would be the email. I mean, even at our company, we use GitHub Enterprise to be able to store our source code. And, we have notifications that our engineers get when, there's pull requests and things like this. And it actually, GitHub identifies each employee as notifications at github.com. That's what that record sends us as its unique reference. And of course, if I marked this as a unique reference, all of those employee records using this pattern would merge. However, what I like about this approach is that, at least I'm given the tools to rectify the bad data when I see it. And to be honest, if companies are wanting to become much more data-driven, as kind of we aim to help our customers with, then I just believe that it means we have to start to shift or learn to accept that there's more risk that could happen. But is that risk of having data, more readily available to the forefront worth more than the old approaches that we're taking?
And for anybody who wants to dig deeper into this idea or learn more about your thoughts on that, or some of the adjacent technologies, what are some of the resources that you recommend they look to?
Yeah, so I mean, I guess the first thing, and Tobias, you and I have talked about this before, is that I think the first thing, the way to kind of learn more about it is to kind of get in contact and kind of challenge us on this idea. I mean, when you see a technology and you're an engineer, and you go out and start using it, you have this tendency to kind of gain a bias around it, that, time after time you see it working, and then you think, why is not everybody else doing this? And actually the answer is quite clear. It's because, well, things like graph databases were not as ubiquitous as they are right now. You can get off-the-shelf free graph databases to use. And 10 years ago, this was just not the case. You would have to build these things yourself. And so I think the first thing is, you can get in touch with me at tiw@CluedIn.com if you're just interested in challenging this design pattern and really getting to the crux of, really, is this something that we can replace ETL with completely? I think the other thing you mentioned, the white paper that you alluded to, that's available from our website. So you can always jump over to CluedIn.com to read that white paper. It's completely open and free to everyone to read. And then we also have a couple of YouTube videos. If you just type in CluedIn, I'm sure you'll find them, where we talk in depth about, utilizing the graph to be able to merge different data sets. And we really go into depth. But I mean, I always like to talk to other engineers and have them challenge me on this. So feel free to get in touch. And I guess if you're wanting to learn much more, we also have our developer training that we give here at CluedIn, which we compare this pattern towards other patterns that are out there, and you can get hands-on experience with taking different data sources, taking the multiple different approaches that are out there as integration patterns, and really just seeing the one that works for you.
Is there anything else about the ideas of eventual connectivity or ETL patterns that you have seen, or the overall space of data integration that we didn't discuss yet that you'd like to cover before we close out the show?
I think for me, I always like when I have more engineering patterns and tools on my tool belt. So I think for me, the thing for listeners to take from this is that use this as an extra little piece on your tool belt. If you find that you walk into a company that you're helping, and they say, "Hey, listen, we're really wanting to start to do things with our data," and they say, "Yeah, we've got 300 systems, and to be honest, I've been given the direction to kind of pull and wrangle this into something we can use." Really think about this eventual connectivity pattern. Really investigate it as a possible option. It's actually that to implement the pattern, you'll be able to see it in the white paper, but to implement the pattern yourself, it's really not complex. It just, like I said before, one of the keys is to just embrace maybe a new database family to be able to model your data. And yeah, get in touch if you need any more information on it.
And one follow-on from that, too, I think, is the idea of migrating from an existing ETL workflow and into this eventual connectivity space. And it seems that the logical step would be to just replace your current target system with the graph database and adding in the mapping for the entity IDs and the aliases, and then you're sort of at least partway on your way to being able to take advantage of this, and then just adding a new ETL or workflow at the other end to pull out of the connected data into what your original target systems were.
Yeah, exactly. I mean, it's quite often we walk into a business and they've already got many years of business logic inbred into these ETL pipelines, and my idea on that is not to just throw these away. There's a lot of good stuff there. It's to really just complement it with this extra design pattern that's probably a little bit better at the whole merging and deduplication of data.
All right. Well, for anybody who wants to get in touch with you, I'll add your email and whatever other contact information to the show notes. And I've also got a link to the white paper that you mentioned. And as a final question, I'd like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today.
Well, I would say a little bit off topic, but I would actually say that I'm amazed how many companies I walk into and they don't know what is the quality of the data they are working with. So I think one of the big gaps that needs to be fixed in the data management market is to be able to integrate data from different sources, to be explicitly told via different metrics. I mean, the classic ones that we're used to would be accuracy and completeness and things like this. For businesses to know what are they dealing with. I mean, just that simple fact of knowing, hey, we're dealing with 34% accurate data, and guess what? That's what we're pushing to the data warehouse to build reports and that our management is making key decisions of. So I think, first of all, the gap is in knowing what quality of data you're dealing with. And I think the second piece is in facilitating the process around how do you increase that? And a lot of these things can often be fixed by normalizing values. If I've got two different names for a company, but they are the same record, which one do you choose? And do we normalize to the value that's uppercase or lowercase or title case, or the one that has a incorporated at the end? And I think that part of the industry just needs to get better.
All right. Well, thank you very much for taking the time today to join me and discuss your thoughts on eventual connectivity and some of the ways that it can augment or replace some of the ETL patterns that we have been working with up to date. So I appreciate your thoughts on that, and I hope you enjoy the rest of your day.
Thanks, Tobias.